Arrhenius acids and bases. Arrhenius acid is any compound that can form H plus in water. That's why we say acids have to start with hydrogen, so that they have the H plus to form in water. Strength. A strong acid ionizes completely. So a strong acid ionizes 100% of the time, so a strong acid is a strong electrolyte. A weak acid ionizes partially. A weak acid ionizes only some of the time, so a weak acid is a weak electrolyte. An Arrhenius base is a compound in water that will form OH-. So we say that bases have hydroxides at the end. However, not all bases are ionic. The one base that you have to know that is not ionic is NH3. NH3 does not have hydroxide, but NH3 is a base. And we'll see why it's a base on the next slide. So a strong base ionizes completely 100% of the time and is a strong electrolyte, just like our strong bases. Strong acids. A weak base ionizes partially or sometimes, so a weak base is a weak electrolyte, just like our weak acids. A Bronsted-Lowry acid and base. Bronsted acid is a proton donor. A proton is simply H+. So the acid gives away its H+, it donates that proton. A Bronsted-Lowry base accepts the hydrogen, or is a proton acceptor. Monoprotic and polyprotic. So mono means one. Protic refers to the number of hydrogens. So monoprotic has one hydrogen. Poly means more than one. Protic means hydrogens. So polyprotic, you have more than one hydrogen to give away. So H2SO4, or sulfuric acid, would be polyprotic. Because it has two hydrogens. In fact, we can be more specific and say that it is diprotic because it has two hydrogens. Acetic acid, or HC2H3O2. Now, even though we have 4 hydrogens total, it's only the hydrogens that are in front of the compound that are acidic hydrogens. Only the hydrogens in front can be donated. So acetic acid is monoprotic because it only has one hydrogen in front. Conjugate acids and bases. Acids give up hydrogens and they form conjugate bases. A base accepts a hydrogen and forms a conjugate acid. So the acid-base equilibrium happens. So the acid and base are just flying the hydrogen back and forth in between each other. So you would start off with an acid. The acid would lose the hydrogen and turn into a conjugate base. Our base would then accept the hydrogen and turn into a conjugate acid. The conjugates could then give the hydrogens back, and so there's an equilibrium set up. So the acid gives it to the base, the conjugate acid would then give it back to the conjugate base. So we're tossing this hydrogen back and forth. So the only difference between them is a hydrogen. The stronger the acid base, the weaker the conjugate. And we like to have the weak conjugates, because if we have a weak conjugate, then the reverse reaction, going from the product to the reactants, is weak and doesn't happen as often or at all. Now, water is amphoteric. Amphoteric means it can act like an acid or base. Water is the only one that you have to be aware of. So when we decide what's an acid and what's a base, we have to look at what water is reacting with to know what it's acting like. So here we have water reacting with HF. HF starts with an H, so it's an acid. When it loses that acid or donates it, it turns into F-, and we would call F- the conjugate base. Water then is acting like a base, and it's going to accept a hydrogen and go from being H2O to being H3O, and that's your conjugate acid. Water is reacting with HClO4. HClO4 is an acid. It starts with an H. When it loses that H, it turns into ClO4 minus, and we would label that the conjugate base. Water then is acting as a base. It will go to H3, and we would call it the conjugate acid. Water is reacting with H2SO4. H2SO4 is an acid because it starts with a hydrogen. It loses one hydrogen at a time, so then it turns into HSO4, and we would call that the conjugate base. So again, water is acting like a base and would go from H2 to H3, and that would be our conjugate acid. Now, even though in these three examples water is a base, water can act like an acid. So that's why it's important to know what it's reacting with.